All right, this is Unit 6, Section 6.4, Sample Means. This will wrap up our Unit 6 um, looking at sampling distributions. So we kind of started with general, we've looked at sample proportions, and now we'll be looking at sample means. And so similar to what we did with proportions, we're going to talk about the distribution of a sample mean. It's going to take on a certain shape, center, and spread, and it's going to have conditions along with it. So if I had a population that I took a sample from over and over and over and took many samples, creating a sampling distribution, eventually what I will start to see is that the sampling distribution shape will become approximately normal. Woohoo! So there's two conditions here. And so remember when we had proportions, the only way that it became approximately normal was if we had 10 expected, at least 10 expected successes and at least 10 expected failures. Now, we're not going to have success and failures with the sample mean. However, there's two things that we can guarantee that it will be approximately normal. The first one is if the population is approximately normal. So if for some reason, and we typically might not know about the population, but if the population is approximately normal, then the sampling distribution will be approximately normal no matter what the sample size is. However, if we don't know what the population looks like or we know the population is skewed, then we won't actually get to a sampling distribution to be approximately normal unless we have a sample size of at least 30. So we would need n to be greater than or equal to 30. This is called the central limit theorem that says even if we pull from a population that's skewed or unknown, once we get to a sample size that's large enough, we will then become approximately normal in the sampling distribution of a sample mean. So there's two pieces there. If we know the population is approximately normal, then we don't care what the sample size is. Just like proportions, if we have an unknown distribution or we know the population is skewed, we need something large enough to get to that approximately normal. So the first thing we look at is shape. The second thing is center. Because the sample mean is an unbiased estimator of mu, the mean of the sampling distribution is equal to the population parameter. So after we've sampled and sampled and sampled and sampled over and over again, it will start taking on this approximately normal distribution and give us what that true parameter is. And this happens as long as the samples are random. And so this is, again, another condition that we have to make sure that we have a simple random sample or a randomized experiment, something that keeps it random. And then our third part here, it says the standard deviation. Once we have approximately normal with a mean and a standard deviation here, we can find this using the standard deviation of all the x bars will be the standard deviation divided by the square root of n. This is assuming independence. So that makes sure that we are not taking, good grief, assuming independence, meaning that one outcome of our sample hasn't influenced the next. Also with that idea of repeats or not repeats, replacement, not replacement. And so assuming independence, or again, we have this idea where it's like, okay, we can always use this as long as we're not taking more than 10 times the sample size, making sure that's smaller than the population. And so we want to make sure this is still true in order to use our standard deviation. And so again, we have these three conditions. So we'll get really good at checking them as we're going, okay, do we have a simple random sample? Do we have independence, or do we need to check our 10% rule? Do we have an approximately normal distribution? We'll start getting in the habit of checking these for both proportions and means. The nice thing is this and this are the same for proportions. So once we've memorized this rule that, hey, we can have this center as long as we have an SRS. Hey, we can use this as long as we have no more than 10% of our population as our sample. These two are the same for proportions. The new part here is that we don't have success and fails like we did in proportions. We just need a large enough sample to become approximately normal. So let's look at our first example. It says the lengths of pregnancies from conception to birth varies according to a distribution that is approximately normal, woohoo, with a mean of 266 days and a standard deviation of 16 days. Okay. Find the probability that a randomly chosen woman has a pregnancy that lasts for more than 270 days. All right, so find the probability, and this is just one randomly chosen, so one observation, lasts more than 270 days. All right, well, we have a normal distribution here, so I will do normal CDF. And then we will go greater than 270, so 270 to infinity, centered at each individual pregnancy has an average expected 266, standard deviation of 16 for my lower bound, upper bound, mean, and standard deviation. And so that will equal, when I put that in my calculator, 0.4013. And so what's the probability that I choose any randomly chosen pregnant woman and her pregnancy goes longer than 270 days? There's about a 40% chance of that. All right, so the next question says, what is the mean of the sampling distribution of X bar for a sample of 6 pregnant women? So now we're not looking at a single randomly chosen pregnant woman. Now we're going to be looking at samples of 6. All right, so when we look here, since the sample mean is an unbiased estimator, the mean of the sampling distribution is equal to the parameter. All right, so we don't need to change anything. The mean of all those X bars, of all these samples of 6 that we would take, is going to equal the true mean. We already know that is 266 days, so we don't need to make a change here. The second question says compute the standard deviation now. Okay, so standard deviation of our sample, X bar. Check that the 10% condition has been met. Okay, so we have a calculation we can do for spread, but it only works as long as we are taking at least 10 times larger the sample size here, or I'm sorry, the population is at least 10 times larger. And so when we look at this, let's check the 10% independence condition. So we would take 10 times our sample and make sure that that is smaller than the overall population. So is it reasonable? And again, I'm leaving this as just a capital N because we don't actually know the exact number of pregnancies at any given day. So on this one, is it reasonable though that there are more than 60 pregnant women out there? Yes. So now since that checks out, we can find the standard deviation with confidence here. So our standard deviation is going to be the standard deviation divided by the square root of n. So again, standard deviation, we had one single pregnant woman had a variation of 16 days. We're going to divide by the square root of that, of our sample size, because as we increase our sample from 1 to 6, it will reduce this variability. So we know we had 16 days for one woman, and then divide by the square root of 6 for the second, or for the 6 women. Now these 6 women, each sample will only vary from the other samples by about 6.5 days. And then the third question, or the fourth question here, is the sampling distribution of X bar approximately normal? Check that the large counts condition is met. All right, so they're telling us, how do we check for a normal? This is our large counts condition. Do we have a large enough sample to make sure that we have approximately normal distribution? So large counts for X bar, we'd need N to be bigger than or equal to 30. Okay, so when I look at that, N is not bigger than 30. N right now is 6, and this would fail. So remember, there's two places here because I get a lot of people that would go, oh, we can't go on. They forget about this condition that says if the population is approximately normal, then we don't have to do anything with the sample size. So even though sometimes we look for a check or an idea here, we can say, is it approximately normal? Because the population is approximately normal, so is the sampling distribution. And so now, again, now we have an approximately normal, woohoo, distribution with a mean and standard deviation here. So the last question says, find the probability that the average pregnancy length for the women in the sample, all right, exceeds 270 days. So now we're not looking at an individual, but an entire sample exceeding 270 days. So now my notation has changed. Where I had an individual earlier, now I'm looking at a whole group. What's the likelihood that I would have an average of 6 people with their pregnancy length exceeding 270 days? So we already checked that it's normal, so we can do our normal CDF. We're still going 270 to infinity for our lower bound and upper bound. But now for our sample mean, okay, so this is where we have to use our two pieces that we've calculated. No change for the mean because it's an unbiased estimator. And we've reduced the variability because we have a group of 6 now. So once I calculate that, I do get 0.271. And so there's not a... So if we were looking at this, it says find the probability that the mean pregnancy length here. So we would say there's a 27% chance that the sample of 6 women would have an average pregnancy length that would exceed 270 days. It's going to be larger variation and more likely for a single woman to go more than 270 days. It's going to be harder as we look at larger and larger samples. So that's why we've reduced that probability. All right, let's look at another example. It says at the Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, woohoo, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average contents weigh less than 16 ounces. So we're comparing the idea of a single observation being less than 16 versus the probability of a sample of 10 jars being less than 16 ounces. And so when we think about this, it's that idea that this single jar is going to have more variability than a sample of 10 jars here. We're going to reduce that variability because we've increased from 1 to 10. So we would say averages vary less than individuals. So it's more likely to find one jar less than 16 ounces than a sample of 10. It's just going to reduce that variability. It's one of those things that if you look at the bag of chips, and I always use this example for averages, but it's this variation. But if you look at a bag of chips and you're like, oh, there's like 3 chips in this bag. I really don't want this. You go back and look for another one. Okay, there's going to be some variability individual to individual, but if you opened up 10 bags, it's not likely that you're going to be really that far off from what they've told you the advertised weight would be. So on the second part, it says, let's actually find those two probabilities. So the individual, so we would find the probability that a single individual is greater than 16. Again, this is a population that's normal, so we can do normal CDF. And we're going to go less than 16. So negative infinity for my lower bound, up to 16 for my upper bound. And then we're going to go with our average of 16.1 for an individual, and the average for, or the standard deviation for an individual would be 0.15. So this would be our mean, and this would be our standard deviation. For the group, this would be an X bar that is less than 16. Okay, if we have a normal distribution here, okay, that means our sample is normal. We can check that condition because it has a normal population. Okay, so we can go to our calculation here, normal CDF. We should go still negative infinity up to 16. Okay, to use the mean that the average of these will equal that 16.1, we need to make sure that those 10 jars were randomly selected, and they tell us that there. So we have a simple random sample, so we can use our mean here. And the third thing that we want to use is our standard deviation, but we need to make sure that we are not taking more than 10%. So we will do 10 times our sample size, which is also 10, and make sure it's smaller than the population, which they haven't told us, but is it reasonable in an entire company that there are more than 100 jars of peanut butter? That seems reasonable. So we can calculate our standard deviation by taking the original 0.15 and dividing by the square root of 10. And so when I calculate that, that's where I get the 0.074. Okay, again, I've reduced that variability by almost half here. All right, so here we should see those two values in my calculator. So I'm going to get 0.0174, and here I have my lower bound, upper bound. I have the average of all the means, and I have the standard deviation of all the means. When I put that in my calculator, I get 0.252. And so it says, yeah, so this is saying which one's more likely, and I think maybe that's what I was looking back at. Averages vary less than the individuals, so I would see that, yeah. So it is more likely to find one jar less than, okay, so it did say more likely, so I think I missed that, but do you see that it is more likely to find one jar that is less than 16 ounces than in a sample of 10. All right, so this is going to be less than the group there. All right, looking at our next example, we have the average texters. So suppose the number of texts sent during a typical day by a randomly selected high school student in the U.S. follows a left-skewed distribution with a mean of 15 and a standard deviation of 35. Draw a possible population distribution for this scenario, okay? So we know that we have an average, it's left skewed, so there's my average here, maybe down just a little bit, standard deviation of 35, so it's got a lot of variation here. So I would have, man, it's probably even further down there where I have 85 and 120 up here, and then maybe I'll take my 50 here and move it down. Maybe my average is really skewed here. All right, so what does this mean about the texting habits of U.S. high school students? It just means that most high school students sends a large number So most high school students send a large number of texts per day. But there are only some that send a small amount. All right, so say you take the average of many simple random samples of 50 students across the US. Okay, so again, the previous two examples, we looked at an individual. We can't look at an individual here because this distribution is not normal for the population. So when we jump to the conclusion here of the simple random samples of 50 students, we need to really make sure those conditions have been met because we have a left skewed distribution. So it says, assuming that our students at our school are typical texters, how likely is it that a random sample of 50 students from your school will have sent more than a total of 1,000 texts in a 24-hour period? All right, so let's check conditions first, just to make sure we've met this. And so the conditions we're going to look for are they random? Okay, so it says random samples, so we're good here. 10%, can we use our standard deviation? Okay, so if we took 50, I'm going to go ahead with 10 times our sample of 50, is that going to be smaller than the population? And so they didn't tell us the population, but is it reasonable that we could say there are more than 500 high school students? Yes, I mean there's even, or in that school, we can totally assume that. And the last one we would look at would be, okay, has it met the large counts condition? Is it normal? Because right now, we can't do this calculation because we don't have a normal distribution. Do we have a large enough sample? Is 50 greater than or equal to 30? So because it meets that, we have a large enough sample here to make it approximately normal. So now we can start to think about this question. What is the likelihood that a sample of 50 students is texting greater than, okay, this is 1,000 for the whole total. So if I take 50 and I divide it into the 1,000, how many are they expecting each student to send a day? About 20 text messages. So what's the probability that a sample of 50 is sending more than 20 on average in a 24-hour period? All right, so we would say normal CDF. We would go greater than 20, so 20 to infinity. We'd have our unbiased mean, so it would still stay at that 15 here. But we would need to adjust our standard deviation. Our standard deviation is going to be smaller than that 35 here. We're going to divide it by the square root of our sample size. And so that's where I get 4.9. 497. And so when I put this in here, now I have my standard deviation, 4.9, 497, and I can calculate it. So what is the probability that a random sample of 50 students from our school will have sent more than 1,000 texts in a 15-hour period? It's about 1562. There's about a 16% chance that we would have a group of 50 students that have sent more than 1,000 texts in the 24-hour period. So a couple things about these examples. If we know we have a normal population, we can find the probability associated with a single observation, with an individual. That's just like what we did in Unit 2 or 3. When we look at now a sample that is not approximately normal, or a population that's not approximately normal, we need to make sure that our sample is large enough by the large counts normal condition to make sure we can use those normal calculations freely. Let me know if you have any questions, and I hope you have a good day. Okay, so I had a question. It didn't make sense to me. Like all of a sudden I was feeling like I was forcing something. If we look back at this example above, I think I have these calculations backwards. I was copying them from what I had written on my notes. And so I wanted us to, these are flipped here. So let me check those again. For the individual, okay, we're saying that this should be more likely to find one jar that's less than 16 ounces. And so the numbers just weren't making sense. Even though I moved on, I was like, something's not working out here. So when I put this in my calculator again, so again, we're going negative infinity to 16, 16.1, and then 0.15. This is where I get the 0.252. So this is a 25% chance that I pick a randomly single jar of peanut butter and it has, or roasted shelled peanuts here, and it has less than 16 ounces in it. When I put it in for the other calculation here, negative infinity, 16, 16.1, and 0.074, which is what we had for our standard deviation of a group. Now I'm getting 0.0882 or 883. Okay, this makes way more sense to me logically. There was something that I was like, this is not right. So in my notes on the paper, I have mixed those two. So I must have done those calculations a little differently. And so I felt like, maybe you noticed that, where I was like, this is not right. Something's going off here. So now this makes sense. We already said logically, it is more likely to find one jar less than 16 ounces. That's what we have confirmed here with our probabilities. This is 25%, this is 8%. It is more likely that we would find one single individual jar that is less than 16 than we would on the group of 10 jars having an average of less than 16. All right, now let me know if you have any questions. Thank you.